This is our second example looking at shear flow. It's another beam in which it's been made of multiple pieces which have been nailed together. So our last example was a I section. This is a box section. So you can see we've got the two web members and then nailed top and bottom at each of those. And then if we go through the question here, it says, we've got a box section which is made up with these dimensions over here. And it says that the largest allowable force that this member can take per nail, the largest allowable force per nail, so for each one of these, is 300 newtons. And so the first thing we need to find is so if each of these individual nails can take 300 newtons, well, what can this whole beam take based upon that, assuming that the other members are all right. And once we find that total shear, well, what is the maximum shear stress in this box section? So this is essentially working backwards from what our previous example was. So in the previous example, we were given an applied shear load, and then we had to determine what the longitudinal shear flow, so the shear force per unit length, the shear flow, was for at a given section, and then we use that shear flow and the nail spacing to determine how much shear load was applied per nail. With this one, we're essentially working backwards. We know how much shear force each nail can take, and then we are going to sort of back out what our applied shear is. So we'll get started. So as I said, working backwards. We know that V nail equals 300 newtons, and we know that the spacing equals 50 millimeters. So 50 millimeters per nail there. And so our if Q is just our shear force per a given length, what we can really do is, well, we have a shear force and we have a longitudinal length. Well, we just sort of plug these in. The only thing that we need to be conscientious of is we have, for a given cross section, a given cut through here, we have two nails. So if we're looking at this plane right here at the top of the webs, we've got two nails there. So we have to account for, essentially we have to double our V nail. So we have two nails, and they can each take 300 newtons per nail, and that's over spacing of 50 millimeters. And if we work all of that out, we find that our shear flow, Q, is 12 newtons per millimeter. All right, and so if we want to find our maximum applied shear force, we can, again, go back to our equation for shear flow based upon our applied shear force, and we see that's just V times Q over I. The next things we need, well, if we, just like anytime we need to find Q, we need to find our centroid, and for I, we need to find I. So those are the two. Let's work those out really quick. So Y bar is just going to be the sum of the areas times the centroidal distance of that little area to the origin over the sum of the areas. So working that out, we've got in our flange, Well, we'll do our, let's see, which one do we want to do first? Well, let's do our flange here. So it's going to be 20 times 120. And its centroidal distance is 100 plus 10. So that'll be 110. Plus, then we have the two webs, so let's just multiply this by 2. They both have the same centroidal distance and area, and that's going to be 80 times 20 for the area. And the distance of the centroid of this piece will just be 60 millimeters from the base here, so 40 plus 20. So we have 2 of those, plus the bottom flange, which is 20 times 120 times 10 millimeters from the centroid to the origin there. And then let's divide by the area. So we have 20 times 120 plus 2 times 80 times 20 plus 20 times 120. If we work all of that out, we get a Y bar equal to 60 millimeters above the bottom flange. And because it's a symmetric section, that's exactly what we would expect. All right, so we're going to work out our moment of inertia. Essentially what we're going to do is find the moment of inertia of the exterior and then subtract out the void, and that will give us the moment of inertia of this box section. So working that out, so we'll just write out the parallel axis theorem just for good practice. That's I sub I plus AI di squared. And that's going to be, so the moment of inertia for the big exterior part is 1 over 12 times 120 millimeters wide times 120 millimeters tall to the third. Because and then the area is 120 times 120. Because the centroid of this big box is at the same location as the centroid by which we're taking the moment of inertia around, the distance to that centroid is 0 squared, so all of that goes to 0. And then let's subtract out the void in here, and that's going to be 1 over 12 times 80 times 80 cubed. So you can see 80 times 80 plus 80 times 80 times 0 squared, because again the centroid of the void which we're subtracting out is at the same location as the centroid by which we are taking our moment of inertia around. So that there is our equation for our moment of inertia. If we work all of that out, we get I equals 1.39 times 10 to the 7th millimeters to the 4th. And so what we want to do is we now have I. We now need to work out, and we have our small q over here. We now need to work out our large q, and that's going to be dependent upon where we take our section. Because we're looking at the shear force in the nail, we want to use the q, which has the bottom starting right at that intersection. So in that case, let's just draw ourselves our picture of what's going on of the section. So at the nailed joint, we'll just draw that's our picture. So that's what our section. It's 120 millimeters wide. We know that the centroid is right in the middle, and so the flanges have a thickness of 20. To the centroid is 40 millimeters from the inside edge of the flange. And so if Q, big Q equals A1, Y1, like I said, because we found the little q, we found the shear flow at the level of the nailed joint, well, then we need to make sure that our section Q here it corresponds to that. And so that's going to be with our distance y to the bottom there. This top flange is going to be A1, and the distance y1. So if this is, section y and y1, y1 is the distance between the centroid of A1 to the centroid of the section. So if we work that out, we get 20 times 120, and that's A1, times 40 plus half of 20 is 10, so 40 plus 10. We get Q equals 120,000 millimeters cubed. So now we have all of the pieces to find our applied shear force if our each nail can take 300 newtons. So if Q, so shear flow, Q, little q, equals V times big Q over I, well, then that is equal to, let's just plug in all of these pieces that we have. So we saw up here that our shear flow was 12 newtons per millimeter. So Q, make that 12 newtons per millimeter. We are looking for V. We saw that Q equals 120,000 millimeters to the third, and that is all divided by I, which is 1.39 times 10 to the 7th millimeters to the 4th. If we do the algebra here, we find that V allowable equals 1.39 kilonewtons. So that means for this configuration, this section, if each of these nails can take 300 newtons, that means that just based upon the nail capacity and that longitudinal shear and that shear flow of 12 newtons per millimeter, the beam can take a load pointing downward, so across, so along, parallel with the webs, of 1.39 kilonewtons. So the second part of the question asks, what's the maximum shear stress in the section for this force V? So it wants to know for this allowable shear force of 139 kilonewtons, what is the maximum shear stress that we would see in this box section? So we know by definition that the maximum shear stress is going to occur at the neutral axis. So really all we have to do is find tau here at the neutral axis. So let's work on that. We'll redraw our section. So we're looking for max shear stress at V allowable. So redrawing our section here. And again, we'll put our centroid. So we've got 20, 40, 40, 20, 120, and these webs here are 20 millimeters thick. So we know our shear stress. So vertical shear stress is going to be VQ over IT. We know V allowable equals 1.39 kilonewtons. So we just worked that out. We know I. We know T. T is going to be 2 times 20 because we've got 2 webs. So that's the total width at a given section. And really what we want to know is we know that the shear stress is max at the neutral axis. So we know the shear stress is max right here. Really all we have to do is find Q. And so Q is just going to be the area above the level that you're trying to find the shear stress. So Q is going to be all of this up here. And it's essentially the sum of A1I times Y1I. So the area of each little piece times the distance of that neutral axis to the centroid for each of those. So for each of these pieces, there's a centroid there, there's a centroid there, there's a centroid there. So there's a distance, we'll call that Y1F and Y1W2 and Y1W1. So sorry, it's a little bit unclear there, but we've got, and then we'll call that A1F, A1W2, A1W1. So the area of this web, the area of that web, and the area of the flange, all above the level that we are trying to find the shear stress at. So that's not too bad. Let's just work that out. So we know the flange is going to be 20 times 120 times, and then Y1 is 40 plus 10. So that's all the flange. That's A1, and that's Y1. And then we need to add in the components from the web. So because they're the same, we can just multiply by 2. They are 20 millimeters wide, 40 millimeters tall. 20 times 40, and the centroid is halfway up, so that's half of 40, so that's 20. And that's the web. And again, so that's 2 webs. A1, Y1. So we maybe call this A1 flange, FL for flange, and we'll call A1W and Y1W, just so that we're super clear and we don't get ourselves confused. So with working, if we work all of this out, we find that Q equals 152,000 millimeters cubed. Well, now we kind of have everything we need. So we've got V, we've got Q, we have I that we found previously, and we have T. So our shear stress is just going to be 139 kilonewtons, or 1,390 newtons times 152,000 millimeters to the third, over I we found over here to be 1.39 times 10 to the 7th millimeters to the fourth. So 1.39 times 10 to the 7th millimeters to the fourth. And now for our T, well, that's 20 millimeters times 2 webs. All right, so all of that we can work out, and what we find, so tau max equals 0.38 megapascal, or if we want, tau max equals 380 kilopascals. And that's it. That's all the question asked from us. So, you know, just from knowing the geometry, spacing of the nails, and how much each nail could take, we could figure out what the allowable load was just from those nails, making sure that those nails don't break, and what does that mean? So if that was the sort of the weak link in the beam, we would be able to find out what the beam could carry. But then for that same beam, we could then work out our shear stress, and we could find out, well, is this timber, will it be able to withstand 380 kilopascals? So that's that question. I hope you found that informative and kind of interesting. Very similar to the previous example, slightly different. Again, we're using a box beam instead of an I-beam. The first example, we were given loads and we looked at, well, what the demands were on the nails. This one, we're sort of working backwards. So that's it for our examples on shear flow and calculating demands on nails in built-up sections.